Okay, now in this lesson, we're going to talk about how we can test for independence in the homogeneity of proportions. So our objectives are going to be to perform a test for independence and perform a test for homogeneity of proportions. So to perform a test for independence, we again use a chi-squared test. The chi-squared test for independence is used to determine whether there is an association between a row variable and column variable in a contingency table constructed from a sample data. The null hypothesis is that the variables are not associated. In other words, the null hypothesis is that the two variables are independent. The alternative hypothesis is that the variables are associated or are dependent. So in other words, for a chi-squared test of independence, the null hypothesis is always the variables are independent. The alternative is that the variables are not independent. The idea behind testing these types of claims is to compare actual counts to the counts we would expect if the null hypothesis was true. In other words, if the variables are independent. If a significant difference between the actual counts and expected counts exists, we would take this as evidence against the null hypothesis. Remember, under the assumption that two things are independent, we have that the probability of E and F occurring is the product of the probabilities P of E times P of F. We can then use the multiplication principle for independent events to obtain the expected proportion of observations within each cell under the assumption of independence and multiply this result by n, the sample size, in order to obtain the expected count within each cell. For example, in a poll of 883 males and 893 females, they were asked if you could only have one of the following, which would you pick? Money, health, or love? Their responses are presented in the table below. Let's determine the expected counts within each cell, assuming that gender and response are independent of each other. Well, first of all, note that I can come up with a total row here. Under the money column, there's 128. Under the health column, we have 1,020. And under the love column, we have 628. Over here, if we add those together, let's see, 82 plus 46 plus 355. Let me grab my calculator here real quick so that I can put those together. Get 82 plus 446 plus 355 is 883. Oh, well, yeah, that shouldn't. It told us we had 883 females, or men, and 893 women. So that total should add up. Okay, so overall then, we have 1,776 total respondents. Okay. So if I wanted to know the expected number of men who think money is most important, assuming that they are independent of each other, it would be the total from the money column times the total from the men row divided by the total number of people that are in the sample. So the expected men and money would be 883 times times 128 over 1776. So we would get 883 times 128 divided by 1776, which would give me 63.64. And in the expected category, it is okay to have a fraction of a person in the expected category. Okay. So we took the row total times the column total divided by the overall total, and that gave me the value that went in the cell where the row and the column overlapped. We could do that for each one of these, and that will be in the next slide. So we've got our totals here. We've taken the value that we had on the previous slide and done our totals. We can then get our relative frequency of men and relative frequency of women, and we get the relative frequency here and a relative frequency there and relative frequency here. And with what they initially said, we're going to take the relative frequency of the column times the relative frequency of the row times the number of observations. Notice that that does give the following relative frequencies. So this is a relative frequency of the column times the relative frequency of the row. If I multiply each of those by 1776, I get 63.58 in a difference of some rounding that I had. It's about 63.6 and 64.29 and so on. So we would get these values by multiplying the column total by the row total times the overall total, or excuse me, divided by the overall total. That is equivalent to relative frequency of the column times relative frequency of the row times the total number of observations. Okay. The expected frequency is again row total times column total over table total. This is a much easier process than coming up with those relative frequencies and everything. We can then do like what we did with the chi-square test of independence. We can see what the difference is between our observed value and our expected value. We can square that difference. We'll divide by the expected value. We'll add all of those up, and we'll have a chi-square distribution. In this case, we have a table that has multiple rows and multiple columns. The number of degrees of freedom is the number of rows minus 1 times the number of columns minus 1. Again, all expected frequencies should be bigger than or equal to 1, and we want no more than 20% of the expected frequencies to be less than 5. Just as what we did in the chi-square test for goodness of fit, we're going to take that chi-squared test statistic we had and compare it to some table value or determine a p-value based off of the row. So again, the process we're going to go through is exactly the same as before. We're going to determine a null and alternative hypothesis. The change here is that our null hypothesis is now talking about rows and columns being independent rather than having a particular distribution. The alternative is that the row and column are dependent. We again choose a level of significance. We calculate our test statistic. It has more cells that we have to work with because now I have multiple rows and multiple columns rather than just multiple columns. I can find a critical value by looking in the alpha column of the chi-squared table and the r minus 1 times c minus 1 row of the table. If we exceed the critical value, we reject. If we do not exceed, we fail to reject. Same way with the p-value approach. We can take that test statistic that we calculated. We can look in the degrees of freedom line that corresponds to r minus 1 times c minus 1. That will then give me a range of p-values that I can then compare to alpha. If the range does not contain alpha or is greater than alpha, then we'll fail to reject. If the range is less than alpha, then we will reject the null hypothesis. We can also use StatCrunch or Minitab or Excel or any number of numerical packages to calculate the exact p-value. On the exam, you won't really be able to do that. You'll have to use the chi-squared table. And then we'll state our conclusion. So let's look at the example that we had here. For 883 males and 893 females, this was the actual observed data that we had. To come up with the expected values, we'll take column times row divided by total to come up with expected values, which we saw in an earlier slide. Our null hypothesis is that gender and response are independent. The alternative is that gender and response are dependent. We've set a level of significance of 0.05. We have our expected frequencies that we calculated. And those expected frequencies are given in parentheses. The actual frequencies are above those. So we have the actual frequencies on the first row of each, or the first line of each category. And the expected frequencies are on the second. We then, again, remember, take observed minus expected. We square that and divide by the expected, and we'll do that for each one of these 6 cells, leading to 6 individual values, giving me 36.82. There are 2 rows and 3 columns, so there are 2 minus 1 times 3 minus 1 is 2 degrees of freedom. If we look in the chi-squared table, under 2 degrees of freedom and the O5 column, we see a critical value of 5.99. Our value of 30.68 or 36.82 is much greater than that, so we will certainly reject our null hypothesis. We will conclude that gender and response are dependent. If we try to find the p-value for this, looking at our chi-squared table, on the 2-row, 36.82 would be way out past this last column. So I know the p-value is much less than 0.001. Because the p-value is less than 0.05, we again would reject the null hypothesis. So no matter if we take the classical approach or the p-value approach, we come up with the same conclusion. There is sufficient evidence to conclude that gender and response are dependent. To see the relationship between response and gender, we can draw bar graphs of the conditional distributions of response by gender. Remember that the conditional distribution lists the relative frequency of each category of a variable given a specific value of the other variable. So if we were to look at the distribution of men, or of these categories, money, health, and love, by men, I would divide each one of these values in the men row by the total number of men surveyed. To get the conditional distribution for women, I would take the number of women in each category and divide by the total number of women surveyed. So that would look like this table. Again, if you add up all of these values, you come up with 1. If you add up all those values, you again come up with 1. Just looking at them, we can see a substantial difference between the two categories. If we put that on a bar chart for men and women, and we look at percents for each category, there's certainly a much different distribution there. The second objective we're going to have is to perform a test for homogeneity of proportions. In a chi-square test for homogeneity of proportions, we test whether different populations have the same proportion of individuals with the sum characteristic. So the procedures for performing a test of homogeneity are identical to those for a test of independence. So the following question was asked of a random sample of individuals in 1992, 2002, and 2008. Would you tell me if you feel being a teacher is an occupation of very great prestige? The results of the survey are presented below. We want to test the claim that the proportion of individuals that feel being a teacher is an occupation of great prestige is the same for each year. So we're comparing proportions for more than 2 years. The null hypothesis is that we have the same proportion in each year, and the alternative is at least one proportion is different. And we're going to use a level of significance for this one of 0.01. We have exactly the same setup as what we had for a test of independence. These are still just categories of variables. One of them is year. One of them is whether or not they think teaching is worth it. So we can still do an expected count for each one of these cells by looking at a row total times a column total divided by the total number surveyed in all 3 years combined. This gives us the observed value and the expected value. From that, we can then calculate our test statistic by taking observed minus expected squared over observed, and then adding all of those up. So there'll be 6 different expressions we'll need to add up, just like what we did in the first example. And here we have 24.74 as the chi-squared goodness of fit, or is the chi-squared test statistic. We again have 2 degrees of freedom. At the 0.01 level, we would have a 9.2 critical value. Where does that come from? We would go to the 0.01 column and the 0.02 row, and you can see 9.21 there. We are certainly greater than that, and we would reject the null hypothesis. Again, with the p-value approach, you could figure out in that 2 degree of freedom row, what's the likelihood of seeing a value of 24.74 or greater? And it ends up being much less than 0.001. It's approximately 0. So again, the p-value is less than 0.01, so we'll again reject the null hypothesis. Doesn't matter if it was a p-value approach or the classical approach. We still rejected the null hypothesis in both cases. So there is sufficient evidence to conclude that the proportion of individuals who believe that teaching is a very prestigious career is different for at least one of the 3 years. So that concludes our discussion of chi-squared test of independence in terms of the concept behind it. I want to go back into StatCrunch, though, and show you how you could use the chi-squared test of or how you could come up with a chi-squared test of independence. So let's take our example that we had here. And let's say we had these 6 values. And again, it's not going to let me copy from my PowerPoint over. So let's try to plug them in this way. We get 418, 602, 479, 541, 525, 485, and this would be 1992. This would be 2002. This would be 2008. And I should have, I guess, my other category here of response is yes and no. Should probably have put that on the other side, but in the working with it, it won't make any difference. I'm going to go to now stat tables contingency. So stat tables contingency with summary. My row labels are in the response column. I'm going to select columns 1992, 2002, and 2008 as the column variables. I'm then, notice that it has chi-squared test of independence already highlighted here. I'm going to go ahead and have it also do an expected count and a contribution to chi-square and hit compute. And what we notice is that we get this table. It shows us the expected count that we did in the slides. The 6.97 represents the difference between the observed and the expected. So it's 418 minus 475.55. If I square that quantity and then divide by 418, so if I take 418 and look at 475.55 and I subtract those, .418 minus 475.55 is minus 57.55. If I square that, I get 3312.0025. If I take that value, and so I'm going to do plus 3312.0025, and I divide by the expected count of 475.55, that gives me the 6.97. So this value is observed minus expected, quantity squared, divided by expected. If I add up all of those contributions to chi-square, I get this chi-squared test statistic of 24.74. I see the p-value is less than 0.001. So it's not quite as obvious as to how to do the test of independence as it was the goodness of fit, because there's not just a test of independence possibility here. I have to work through it a little bit. I have to go to tables, contingency with summary, and then I can go through the process of picking what I'd like. So that concludes section 12.2.